Section 5.6, example 23. Um, so using the ratio test for each of the following series, use the ratio test. Okay, so ratio test tells us to look at the kth term versus a k plus 1th term. So we're going to take the limit as n approaches infinity of a sub n plus 1 over a sub n, taking the absolute value of that. And then if rho, we call that value rho, if rho is between 0 and 1, then we converge absolutely. If rho is greater than 1, then we diverge. And if rho is equal to 1, it's inconclusive. So let's take a look at that. So we're going to take the limit as n approaches infinity of a sub n plus 1, so the n plus 1th term. Let's see, so 2, we'll say n plus 1 over n plus 1 factorial over the nth term, so 2 to the power n over n factorial. We're taking the absolute value of that value. And all of these numbers are positive, so we could actually drop the absolute value here. I'm going to do our keep, change, flip. So we have 2 to the n plus 1 over n plus 1 factorial. And we're multiplying that with the reciprocals. So n factorial times 2 to the n. So let's take the first term out of here. So remember, if we have like 5 factorial, that's going to be equal to 5 times 4 times 3 times 2 times 1. So us looking at this starting point, the next one, we have like n plus 1 times n plus or n minus 1 all the way up to 1. So we could just leave it as this, stop here, because now we have something that we could divide out. And we're going to do something similar to that too. So let the limit as n approaches infinity of 2 to the power n times 2. And let's multiply that n factorial in the numerator. Down here, we are going to have n plus 1 and times n factorial. Now we have something that we could divide out, and that 2 to the power n. So n factorials divide out, 2 to the power n's divide out. And now we're left with the limit as n approaches infinity of 2 over n plus 1. And that 2 over n plus 1, as n approaches infinity, this goes to 0. So now what does 0 mean? So 0 less than or equal to rho less than or equal to 1 converges absolutely. So since rho is equal to 0, this implies that we converge absolutely. So converge absolutely. So we have that. Let's move on to the next one. All right, so again, we're going to look at a sub n plus 1 over a sub n. We're going to take the limit as n approaches infinity and see what we get. That value is going to end up being rho. So the limit, let's write it down here. The limit as n approaches infinity of the n plus 1th term. So we have n plus 1 to the n plus 1 over n plus 1 factorial. We're dividing that by n to the power n over n factorial. And absolute values. Since all of these values are going to be positive, we could drop the absolute values. So that's going to be limit as n approaches infinity. Here we have n plus 1 to the n plus 1 over n plus 1 factorial. And here we have n factorial n to the n. All right, so to get these to look similar, I don't want to make them look similar. What we could do is get rid of one of these. So now we could have this divided by this with the same exponent. So let's do that. And let's get these two to look at least similar so that we could divide stuff out too. So the limit as n approaches infinity of, we could factor out at n plus 1. And then we have our n plus 1 to the power n. And we have n factorial here. In the denominator, we have n plus 1 times n factorial times n to the power n. Lots of things divide out. So we have these two dividing out. We have these two dividing out as well. And we have the limit as n approaches infinity of n plus 1 over n to the power n. We could bring these two under the same parentheses. And let's see. We could separate the numerators, or the numerator, since we're adding, we could separate those two into two fractions. So we have the limit as n approaches infinity of 1 plus 1 over n to the power n. And what does that do? So earlier in this chapter, I want to say in chapter or section 1, we went over something that looked like this as n approaches infinity. This entire thing ends up going to E. This is Euler's number. Ooh, but I know that Euler's number is greater than 1. It's like 2.7 something, somewhere around there, or 2.37. It's 2 point something, which is still greater than 1. And because it's greater than 1, this diverges. Since rho is greater than 1, this implies that a sub n diverges. All right, and let's take a look at this last one. Ooh, this looks fun. All right, so we have the limit as n approaches infinity, and or a sub n plus 1, so the second term. So we're looking at the absolute value of -1 to the n plus 1th term. We have n plus 1 factorial squared over 2 times n plus 1 factorial. And in the denominator, we have -1 to the power n. And we have n factorial squared over 2n factorial. Since we have these absolute values, we could drop the absolute values and absolutely drop these here. The rest of this in here is going to end up being positive. So we have the limit as n approaches infinity. So again, these divide out, we could drop the absolute values as well. We could do a little keep change flip. So here we have n plus 1 factorial squared over 2n plus 2 factorial times n factorial squared. Oh, no, it should be in the bottom. N factorial squared 2n factorial. All right, so what we want is a 2n factorial. We could take the first two terms of this factorial out. We could simplify this factorial as well to make it look a little bit more like this. So limit as n approaches infinity. We could take an n plus 1 out, leaving us with n factorial. That whole thing is squared, which we have n factorial squared here. Okay, so we're good there. And we're multiplying that by 2n factorial. In the denominator, the first term we take out of the factorial, 2n plus 2. The next term we could take out is going to be 2n plus 1. The next number we take out is going to be 2n. And we could stop there because we have a 2n factorial up here. So 2n factorial, 2n factorial. Let's, the 2 or n factorial squared. Oh, I didn't write it. N factorial squared is here, but we still have that squared on this part here. Limit as n approaches infinity of, I'm expanding that, n squared plus 2n plus 1, and multiplying these two in the bottom, 4n squared. So we have 2n plus 4n is 6n plus 6n and plus 2. And now we can multiply both top and bottom by 1 over n squared, leaving us with the limit as n approaches infinity of 1 plus 2 over n plus 1 over n squared over 4 plus 6 over n plus 2 over n squared. As n approaches infinity, that goes to 0, 0, 0, 0. So we end up with 1 over 4. Since 1 over 4 is less than 1, but still greater than, actually, we don't have to worry about greater than 0. It's less than 1, so this tells us that the series converges. So converges, converges absolutely. And there we go. If you have any questions, please feel free to ask. Otherwise, bye.